Good morning, everyone. Today, let's talk about standard electrode potentials in electrochemistry. So we're going to use an analogy here for electricity flow through a metal where we are going to use the flow of water through a pipe because you have a better understanding of that than electricity, which is somewhat magical. I know at least it is in my mind, but here we have a quantity of water that can be measured flowing through a pipe. You can measure the quantity of water in liters. Well, in electricity, we're going to measure the quantity of electricity by charge. We're going to use coulombs. And the flow rate of water would be the amount of liters passing through the pipe per second, whereas the flow rate of electric current is going to be measured in amperes, amps for short, or charge in coulombs per second. Just like liters per second for water, for electrical flow, it's going to be coulombs per second. And of course, those flow rates depend on the pressures at the beginning and end of the pipe of water. And in this case, the pressure of electrons flowing through a circuit is really measured by potential difference, which is voltage. So that's the joules per coulomb is the pressure pushing the electric current through the circuit. Now, cell voltages are potential differences. They can be precisely measured in an operating electrical cell, but potentials for individual electrodes cannot be measured because they're in isolation by themselves. There's no electricity flowing through a half cell. So in order to establish the voltages of cells, we have to complete the circuit. And for this, we use a standard hydrogen half cell. And a standard hydrogen half cell is a half cell where hydrogen gas is pumped through a solution of acid, 1 mole per liter acid with an activity of 1. We have a platinum electrode that where the voltage is applied, and the hydrogen gas, as you can see, flows through the solution and is bubbled through the solution. Now, again, this half cell, we can't measure the voltage of this half cell, but we are going to establish it as 0 for a reference point. So when we connect another half cell to this standard hydrogen half cell, we can arrive at a voltage which can be measured. And to give you an example here we have we have a functioning cell here involving half cells of the standard hydrogen half cell and copper. And in the first example on the left, you can see that the copper metal has a stronger pull on electrons than the standard hydrogen half cell. So the electrons flow towards the copper. On the other side, we have another functioning cell made up of 2 half cells. The standard hydrogen half cell in this case has a stronger pull on electrons than the zinc does. So the electrons flow from the zinc to the standard hydrogen half cell. Now, the way to determine this, of course, is the sign of the voltage. You will get a voltage that is negative when the electrons flow away from the metal, in this case zinc, towards the standard hydrogen half cell, and you'll get a positive voltage when the electrons flow from the standard hydrogen half cell to the other half cell. So typically, you can access these values for half cell voltages from standard electrode potential tables, also called reduction potential tables, because in this case, these reactions are all written as reductions. We're showing gains of electrons, and the higher up you go in the table, the stronger the pull on electrons. And you can see here our reference cell is for arbitrarily established as 0. Anything that has a voltage higher will have a stronger pull on electrons. Anything with a voltage lower than 0 or negative will have a weaker pull on electrons. So again, to summarize, our standard hydrogen half cell can be used to determine voltages of other half cells. And when they are, all the gases will be at 100 kilopascals or 1 atmosphere. And if there is no metal that's been identified, we're going to use an inert metal like platinum as an electrode to act as a surface area for the reaction to occur at. And as I've mentioned previously, the copper metal here, the copper ions have a stronger attraction for the electrons, so the electrons flow from the standard half cell to the copper. And the zinc metal on the other side has a weaker pull on electrons, so the electrons flow from the zinc to the standard hydrogen half cell. So now let's calculate some of these cell potentials for electrochemical cells, fairly basic calculations here. To determine the cell potential for an electrochemical cell, we're going to use tables. We're going to use standard voltage tables, also called E0. And we are going to combine the two to create an overall voltage. And when we do, we're going to ensure that the number of electrons transferred is the same for both the oxidation and the reduction reactions. But when we do multiply half cell reactions, we aren't changing the voltages because the pressure flowing through that circuit is going to be the same regardless. So we are going to find the standard voltage values for each half cell and then use them to determine the overall voltage of the whole cell. So for a redox reaction to be spontaneous, the sum of the half reactions have to result in a positive value for the cell. If it doesn't result in a positive value, then that particular cell will not spontaneously run and will not produce a voltage. Those types of cells are called electrolytic cells, in which case you use electricity to actually drive a chemical reaction rather than derive electricity from chemical reactions. So here is an example of a standard reduction potential table. You can find these in books, and when given questions where you're asked to solve for voltages of cells, you will always be given either access to the values of these standard voltages for half cells, or you will be given a table. Now notice that the best oxidizing agents are at the top left, and the best reducing agents are at the bottom right. You get the maximum voltages by taking really strong oxidizing agents and combining them with good reducing agents. That will give you the maximum voltages for cells. So now let's look at an example here. We have an example of a cell with a salt bridge that is potassium nitrate. We have zinc and we have copper. And we are going to now locate these two potential reductions in a standard reduction table. So here's our standard reduction table, and we can see that the zinc reduction is zinc 2+ ions combining with 2 electrons to make zinc, and the copper 2+ ion combines with 2 electrons to make copper. Since copper 2+ ions have a higher value, that the copper 2+ ions will steal electrons from the zinc. So the zinc is going to be oxidized, and the copper 2+ ions will be reduced. So to show that, the electron flow will flow from the zinc to the copper. So what we're going to do when we combine these two voltages is we're always going to flip the lower voltage because it has a weaker attraction for electrons, and we are going to change the voltage as well. And if the number of electrons transferred is different, then you're going to have to multiply these half reactions to balance the number of electrons that are transferred. And we'll do that in other examples. So in this example, there's no need to do that. So when we look at the voltages from the table, we get voltages for the copper and for the zinc, and the overall reaction can be determined by simply adding those two half reactions. And when we do that, we get the overall reaction. Notice the electrons canceled here. So copper 2+, as I mentioned, has a stronger pull on the electrons, and it's reduced, and the zinc metal is being oxidized to zinc ions. So now, when we determine the voltage of the cell, we are going to reverse the voltage of the zinc because it is being oxidized, not reduced. And when we simply add those two voltages together, we get the voltage of the entire cell from each half cell voltage. And in this case, it's 1.10 volts. So you think of it as a number line, and you're simply measuring the distance from 0.34 volts to minus 0.76 volts, which is in fact a difference of 1.10 volts. So now let's do another example here. Let's look at a half cell involving ferric ion changing to ferrous ion and copper being changed into copper ion. So we are going to answer these questions. So again, we're going to use a table, and we locate. Now, please make sure you locate the correct half cell, because note that there's an Fe2 plus 2 electrons making iron. Don't use that one, because we can see in this case, we are simply changing ferric ion to ferrous ion. So in this half cell, we have ferric ion changing to ferrous ion. That's the correct half cell voltage to use. And copper changing to copper 2 plus ion, we can see it has a weaker pull on electrons. It's below the ferric ion changing to ferrous ion. So now we can combine these two. Again, as mentioned before, we have to balance the number of electrons flowing through this circuit. So the first equation here only has one electron, so we are going to have to double it. So we double the first equation here, 2 ferric ions and 2 electrons combine to make 2 ferrous ions. And the voltages, again, are 0.77 volts. Notice we've changed the 0.34 volts into a minus because it's being oxidized, not reduced. And the difference is 0.43 volts. So the overall equation is ferric ion is being changed into ferrous ion. It's being reduced. And the copper metal is being oxidized into copper ions. And we can identify the oxidation and reduction. And by convention, oxidation always happens at the anode in a galvanic cell, which is a spontaneous cell that produces electricity. And reduction always happens at the cathode. And we can also identify, since copper is oxidized, we call it the reducing agent. And since ferric ion is reduced, we can call it the oxidizing agent. So let's try one more example. And what I would do is stop the video and do this one on your own. Okay? Answer these questions. And now I'm going to answer them for you. So here we have, again, we're seeing that ferric is combining with an electron to make ferrous. Its voltage is 0.77 volts. We can see that permanganate, MnO4 minus, changing into Mn2 plus ion. We find a half cell in a table that has this particular reaction. Note that there's also hydrogens involved. There's also electrons involved, and we get the voltage. Again, when you're asked to solve a problem like this, you will either be given a table or you'll be given the standard voltage of that particular half cell. You can't solve it without that information. So we are going to now recognize that the voltage is higher for the permanganate changing into Mn2 plus. Therefore, it will be reduced. And the other equation, the ferric ion changing to ferrous, in fact, is not going to happen. It is a smaller voltage. It has a weaker pull on electrons. So it, in fact, is going to be oxidized. So we are going to change its sign. We also recognize there's 5 electrons in equation 2. So we have to multiply equation 1 by 5. And now we're ready to combine these two equations, half equations together, these two half reactions. And note that we change the voltage again from a positive to a negative since it's being oxidized and not reduced. And when we add these two up and cancel out the electrons, we end up with this as our overall reaction. And the voltage, the difference in those voltages is 0.74 volts. It's a positive voltage. So it's a galvanic cell that will spontaneously deliver electricity for us. So the oxidizing agent is the permanganate ion, and the reducing agent is the ferrous ion. And we can write this again by convention. We show the oxidation first, and we show the reduction second, and that indicates the presence of a salt bridge. Now, let's talk about how Gibbs free energy gets involved. So Gibbs free energy, when we study the expansion and compression of gases, remember we could calculate the amount of work done by pressure volume changes. So the work done on the system is positive, and the work done by a system is negative. So again, if the work is done on the system, it's a positive work. The work is done by the system, it's a negative work. And in electrochemistry, we don't cause pressure volume changes, but we can force electrons through a circuit against a resistance. And that's the type of work we do when we create electrochemical cells, galvanic cells. So in a system like this, what I'm showing here in the picture, where we have silver and copper reacting in a test tube, the system there's no work being done here. Why? Because, well, the system is at equilibrium. The rate at which silver is forming and the rate at which copper is forming, the copper ions are changing. In this case, there are silver ions changing to solid silver. The rate at which those reactions are happening are equal. They're at equilibrium. So no work is being done. So now let's talk about an example where work is being done. In this case, we have an electrochemical cell, a galvanic cell. We have copper metal is being oxidized to copper ions. Silver ions are being reduced to silver, and electrons are flowing. In this case, the cathode has a stronger pull on electrons than the anode, so the electrons flow from the copper to the silver. And we can also see the salt bridge is essential. Again, we talked about this a few lectures ago. Without a salt bridge, this reaction would not happen, because as copper ions are being created, we have to maintain the electrical neutrality in this solution. To do that, we need a flow of negative ions. In this case, sodium nitrate is in the salt bridge, so negative ions will flow in to neutralize the copper 2+ ions. Otherwise, you would get a buildup of positive charge here near the surface of the electrode, and that would, of course, that repulsive effect would stop those half reactions from happening. Similarly, in the other test tube, or beaker rather, you're going to get silver ions being consumed, so we have to replace the positive ions being lost. So to do that, we're going to get sodium migrating from the salt bridge, and eventually you should end up with copper flowing all the way. The copper ions are going to flow all the way into this cell. So that's a little summary of what's happening here. So the electrical work is done by pushing a charge through an electrical resistance. And we can determine that by multiplying the charge by the voltage, where Q, again, is a symbol we use for charge. And the voltage is delta E, which, remember, a volt is really a joule per coulomb. So when we multiply a joule per coulomb by a coulomb, we end up with a joule. So a joule is really defined as pushing a charge of 1 coulomb against a resistance of 1 volt. Now, if work is being done, it's a negative value. Work is being done by the system on the surroundings. That's the definition of a galvanic cell, essentially. And if the work that's done is positive, we call those electrolytic cells. Those are cells in which electricity is used to drive chemical reactions. An example of that would be the manufacture of chlorine gas from sodium chloride, a very common industrial process, because chlorine is a very useful oxidizing agent in cleaning water. We can mass produce chlorine from electrolytic cells that use electricity to drive the reaction in the reverse direction. So we can, and salt, of course, sodium chloride is abundantly available all over the world. Wherever there's been ancient seabeds that have evaporated, they have left behind large deposits of sodium chloride, mixed with other chlorides, of course. And we can use electricity to drive that chemical reaction and change the chloride ion into chlorine gas. I know at the factory I worked in Cornwall, the other reaction they drove using electricity was to make sodium hydroxide. They would take the sodium chloride salt and they would make chlorine gas out of it, and they would also make sodium hydroxide, which is a widely used industrial chemical. Now, the work that's generated can be determined by taking the charge and multiplying it by the voltage. Recall that another way of calculating Q is to multiply current times time, I times T. So we get a couple of variations of that equation. And I, again, is the current, which is measured in amperes, or amps for short, which is really a coulomb of charge per second. And the time is measured in seconds. So if you get time in units of minutes or hours, then you change it into seconds. So here's an example. I have a 6-volt battery delivering 1.25 amps for 1.5 hours. Let's calculate the total charge passing through the circuit and the electrical work done by the battery. So here's our solution. We have 1.25 amps of current. We have a voltage of 6 volts. And the time is 1.5 hours. And I've said previously, we are going to convert the times into seconds. So to do that, we multiply by 60 minutes per hour and 60 seconds per minute, cancel out the minutes, cancel out the hours, and we end up with 5,400 seconds in 1.5 hours. So the charge is the current multiplied by the time, 1.25 amps, multiplied by 5,400 seconds, gives us 6,750 coulombs, which we can express again to 3 significant digits of 6.75 times 10 to the 3 coulombs. So now the amount of work that's done is to take the coulombs and multiply it by the voltage, and it's a minus, it's work being done. So it's 6,750 coulombs multiplied by 6 volts, which was given in the question, and we end up with minus 4.05 times 10 to the 4 joules of work done. The cell is producing electricity and is doing work on the surroundings. Now, Gibbs free energy and electrical work. Delta G, recall, it's a spontaneous chemical reaction at constant temperature and pressure. It's also related to the maximum amount of electrical work that's done by a galvanic cell. So delta G is always equal to delta H minus T delta S, where delta H is enthalpy change, delta S is entropy change, T, of course, is the temperature at which it's happening. So the maximum amount of useful work that can be obtained from a reaction, delta G, will be equal to work max. So, but the chemical work is turned into electrical work in the cell. So the work, the maximum amount of work is the maximum amount of work that has been driven by that electrochemical cell. Therefore, the delta G is equal to the work done by the electrical cell. So we can calculate it by the charge minus Q times the voltage, delta E. Remember, charge can also be calculated by the current multiplied by the time. And we can also calculate it from the number of electrons that are being involved times a Faraday, which is the charge on a mole of electrons. So again, Q is charge, T is time in seconds, and delta E is the potential difference or voltage of our galvanic cell in this case. And a volt, remember, is a joule per coulomb. So this quantity will be given to you on an information sheet. You're not required to memorize it, so you will be allowed to use this value, of course, when calculating work done and delta G. So N, again, number of moles of electrons transferred during the reaction. So you have to balance the 2 half-cell reactions with respect to electrons to make these calculations. Now the reaction is spontaneous if delta G is less than 0 or delta S, entropy change is greater than 0. So in summary, delta G is equal to the work done by the electrical system. It's minus Q times delta E. Minus Q is the charge, delta E is the voltage. Or we can calculate it from the number of electrons flowing times the Faraday, which is the charge on a mole of electrons, times the voltage. Or we can calculate it from the current times time times voltage. So reactions in which reactants and products are in their standard state. We can calculate delta G under standard conditions using the voltage under standard conditions. So here's an example. So we have a zinc half cell, which is changing into zinc 2+ ions in a 1 molar solution of a soluble zinc compound like zinc nitrate. Remember, all nitrates are soluble, so frequently in electrochemical cells, of galvanic cells, we use nitrates. And we have copper ions from copper nitrate being reduced to copper. Remember, we show the oxidized substance first, reduced substance second. Now, because it's under standard conditions, it's operating at 25 degrees Celsius. The cell voltage is 1.1 volts, which you could easily calculate from the half cell voltages of zinc and copper. Zinc ion changing to zinc and copper ion changing to copper. In this case, the copper 2+ has a greater reduction potential than the zinc 2+. So the zinc ions, zinc is actually being oxidized, not reduced. It's the copper 2+ ions that will be reduced because they have a stronger pull on electrons. So we are now going to calculate the delta G under standard conditions, delta G naught for this reaction, if I dissolve 1 mole of zinc. So here's our solution. So zinc is oxidized as zinc 2+ ions plus 2 electrons. That voltage is minus 0.076. And because it's being oxidized, we're gonna reverse the sign from a minus to a plus. And the copper 2+ ions, as I said, have a stronger reduction capability. They have a stronger pull on electrons. They're going to pull the electrons away from the zinc electrode. The voltage of the half cell for copper 2+ changing to copper is 0.340 volts. And when we combine these two equations, we see that both involve 2 electrons, so no need to multiply them. And if you did, you wouldn't multiply the voltages. The voltages always stay the same, regardless of how you manipulate the half cell reactions. But the voltages here, the difference, we're going to get on a number line. If you went from 0.3 to minus 0.076, you're going to get a voltage of 1.1 volts under standard conditions for a cell created from zinc changing to zinc ion and copper ion changing into copper. So the delta G can now be calculated. We can see there's 2 moles of electrons involved in this process. So we're going to take the minus value of those 2 moles, multiply it by a Faraday, which is the charge on a mole of electrons, and then multiply it by the voltage. Remember, volts are always joules per coulomb. So when you make these changes, you end up with canceling the coulombs, you cancel the moles, and you end up with your value in joules. In this case, the delta G is minus 2.12 times 10 to the 5 joules per mole of reaction, in this case, per mole of zinc dissolving. Now, suggested homework. Read Petrucci and do these problems in Petrucci. Thank you very much. We are now going to